Hi everyone, my name is Tong Kaweewut here. I'm a CEO of SCB 10X. Today, it's my pleasure to moderate the session here with Dan Fu, VP of Kernel at Together AI, one of the fastest growing unicorns in Silicon Valley. Hi Dan, thank you so much for being here.
Hi, thanks so much for having me. It's a real pleasure to talk with you today.
Yeah. So maybe let me start by inviting you to talk a little bit about Together AI, like what's the product and service that you are currently offering, because most of the people might not know Together AI well.
Yeah, so Together AI is a AI native cloud. So we offer the full suite of cloud services for AI native companies and startups from renting out GPU clusters for folks who are training their own models, all the way on the other end to hosting open source inference of models. So we can serve everyone from the frontier labs training their frontier models to AI application developers who just want an API to call the models. And the really exciting thing is we're seeing a lot of customers start to go kind of end to end on our platform. So people who will train on our cloud and then want to deploy on the cloud and scale up and scale out that way.
Yeah, thank you. That's very interesting. So let's talk a bit about your roles right now. I understand that you wear two hats as an assistant professor at UC San Diego and also the VP of Kernels at Together. How does this dual perspective help you bridge the gap between the breakthrough algorithms and your production ready systems?
That's a great question. And so at Together, we are really, I think, a research-driven and research-focused company. And one of the reasons for that is that AI and GPUs in particular are such new compute and such new algorithms that you really have to work hard on figuring out how to optimize them. So our customers will say that their workloads run faster on Together's cloud than they do on other clouds. And that's not because we have better GPUs or anything like that, but it's because we spend a lot of time making sure that our customers have the right software stack, the right kernels, the right algorithms to really get the most out of the hardware. That really plays into our deep research connections. So we have something like 10 or maybe even 12 now professors at the company who are working full time,
Hmm.
and we generally take our research programs that we have developed in academia over the years, and we're now taking them and building out real production use cases. So my lab at UCSD does a lot of work on new kernels, new algorithms to make machine learning models faster, and then we will go and talk with customers and figure out how to deploy them, figure out the places where they can really make a real impact.
Yeah, seems like a lot of synergy there. So, so the flash attention has become a cornerstone technologies in the production AI systems today. So, can you walk us through the journey from the academic research to the deployment at the major tech companies, and what kind of lessons that taught you about scaling research breakthroughs?
Yeah, that's a great point there. So the story of FlashAttention, I think, starts back around 2022-ish. This was back in our PhD lab. Me and Trida were in the same PhD lab, and we had done a bunch of work on trying to make transformers and machine learning models faster using just pure machine learning algorithmic techniques. And this curious thing kept happening where we would propose these new techniques. There's a lot of sparsity, low rank work, and we would do all this work. We would say like, oh, you can get rid of 90% of the compute in the transformer. And then you'd see like a 1.5x speed up or something. So you'd be getting rid of all this compute, and then not seeing actually the wall clock time go down. So what we ended up doing is we ended up taking another look at it, and we realized that this attention algorithm, these transformers, are actually not really bottlenecked by the pure amount of compute that they're doing. They're actually bottlenecked by other things like I/O on the GPU. So you can think about it as the GPU's equivalent of the disk. We were doing a lot of reading and writing from GPU HBM is what they call it. So with flash attention, we realized, hey, there are some really classic systems techniques going back to really almost the databases literature from the 70s and the 80s about how you can compute this attention algorithm better. And we were able to take that, make attention 2 to 3 times faster, and then also be able to scale attention to long context. So before that, I think the longest context models that were being trained were something like 2,000 context. I think that's like 4 pages of text. Now, with after FlashAttention and all the adoption that it's seen, we were able to scale attention up much longer. Now you see models with much longer context lengths. I think the lesson there for the academic research side is to really look at those final metrics that you're really trying to optimize, and we also spent a lot of work just trying to make sure that FlashAttention was usable, and making it relatively easy to install. And as a result, now it's been adopted by, I think, every industrial lab has used FlashAttention, or at least their own version of FlashAttention. And there's been a lot of work since building on it since back then as well.
Yeah. And also your ThunderKittens framework also makes the GPU kernel development accessible to students, with no
Yeah.
CUDA experience, and yet achieve 10 to 40% performance improvement. How do you balance the simplicity with the performance when building the infrastructure tools like that?
Yeah, it's a great question. I think the real story with ThunderKittens was we had observed that every time there's a new hardware iteration, it was actually taking quite a long time to build out the best kernel. So between Hopper being introduced and FlashAttention 3, which is eventually the fastest version of attention on Hopper, it was kind of a 2-year development cycle. So we were trying to figure out, is there some way to make things more easy to adapt, or easier to develop in new hardware. And ThunderKittens was our first attempt at this. So it really takes some basic abstractions that we found were really useful in developing FlashAttention, a few other things like fast kernels for state-space models and things like this. And trying to figure out what are the right abstractions. So as a result, when the Blackwells came out, we were able to match NVIDIA's best gen performance within, I think, 2 weeks of it coming out. We were able to match their fastest attention kernels, fastest gem kernels, pretty quickly. And we've been able to just develop kernels at a much faster pace. So I think that's great, not only for students, it's really great for students to onboard, but we also use it in production together. So turns out, when you have the right abstractions, you can also take world-class kernel engineers and make them just that much more productive, because they can just produce kernels much faster than they were able to before. So now we have ThunderKittens kernels really pushing the frontier of what you can do with hardware and software co-design.
Yeah, that's very interesting. I think maybe we shift gear a bit. Maybe we talk about how we're scaling the infrastructure for enterprise. I think for the sake of full transparency, SCP-10X also a happy customer of Together AI. It helped us reduce the cost of inference, at least 30%. So we're very happy about it. So Together AI now serve over like 450,000 developers, and a major enterprise right now, like Salesforce and Zoom. What are the big infrastructure challenges you face when you implement all of this, and when moving from serving researchers to support kind of business critical applications? Seems like there's a lot of things happening around research going to the enterprise. So can you talk a little bit about that?
Yeah, that's a great question. I think the number is actually now 1 million. So we somehow have 1 million developers on the platform, which, when we started this thing 3 years ago, is I think not something any of us was anticipating. The real challenge, I think, with scaling GPU infrastructure is that you are trying to scale something that is sort of fundamentally unreliable. So it's not like a CPU where you can kind of just expect your CPU to work. It's kind of relatively rare, maybe not at huge scale, that a CPU will crash. But a GPU, the GPUs will fail at a much higher rate than CPUs even. And they can fail for all sorts of reasons. So they can fail because, the drivers are unstable and there's some bug that encounters and suddenly a bunch of GPUs fall off the bus. They can fail because, sometimes we are in the United States and across the world building out these really big new data centers. And that build out is happening very rapidly. So sometimes there's just a new data center, and there can be a power cut, or there can be a fiber cut, or something like that. So really the thing that we need to do it together is how to figure out how to insulate customers from those kind of real
Mhm.
world complications. So we'll do things like we'll put customers across multiple clouds, across multiple data centers. So if you're serving inference and the fiber gets cut in some data center somewhere, you can still be serving your inference. Or if you're serving training, you can still have productive work going on even if something like that goes on. We do things like hot spare. So if a GPU falls off the bus in one node, we can just really quickly swap that out for another rack, another set of nodes. We have cold spares on site. So sometimes the hardware is very new, it's being refreshed very rapidly. Sometimes it just breaks. So maybe the NV switch goes out or something like that. We have cold spares on site so that we actually have people on site who can go and swap out the physical pieces of hardware. Like if the wire breaks, you have to go replug the wire. So we really try to think through, what are all those things, and that's because we are a research driven, AI driven company. We know what the AI workloads look like. We know what it means to have downtime in this in this really fast moving industry. So we try to build the systems and the resiliency that we would want if we were building out those AI apps ourselves.
Okay, so it seems like the continuity and the kind of backup plan is very important for, the business, So that's very interesting. And with your recent Series B funding, Together AI is now expanding with the NVIDIA Blackwell GPUs. How do you approach the
Yeah.
hardware software co-design when you're planning the
Yeah.
infrastructure?
Yeah, that's a really great question. I think the Blackwell GPUs are really exciting. We've seen
Yeah.
that they're really getting faster and they can do things like FP4,
Mm.
and there are actually models that are designed for FP4. So that means that the weights in the model really only have 4 bits in them. So there's relatively few numbers that they can take, and yet the models can still have really really good performance. I think some of what we're seeing is just helping customers get the right kernels in place. So we are still relatively early in the cycle. So if you just take your old code that was optimized for Hopper and run it on Blackwell, it might not always run as fast out of the box. We can help customers overcome that kind of software kernels hurdle. So that's the first bit. The second bit is that we can work with customers to really design their models explicitly for Blackwell. So there are models like DeepSeek's MLA, the DeepSeek models that are really hyper specialized for Hopper based on kind of how they design the attention module. We can work with customers to figure out what does that look like for Blackwell? What is the right design point for this new generation of hardware? Or how to use some of the new quantization features like these microscaling precision, these new microscaling precision. So yeah, we're really excited about all of these, and it's kind of how we bring that added value. So we're not just a GPU platform. We don't just give you GPUs. We also help you figure out how to use them and get the most out of them.
Yeah, interesting. Not just giving the GPU, but giving the way how to use the GPU effectively as well, right? So that's very important.
Exactly. Yeah.
So, and you also mentioned before that the custom kernels often fail to meet these theoretical performance thresholds. But for the enterprise teams, now they are reevaluating their AI infrastructure. Like, how should they think about the trade-off between this off-the-shelf solution versus the customs? It seems like a big question here.
Yeah, that's a great question. I think you don't necessarily see all the time that kernels will fail to meet some performance expectation or something like that. I think what you'll see is that there's actually a lot of great kernel work out there in the open source right now, but it might not always be clear in what circumstances they work. So sometimes maybe you can get out of the regime where it was designed, and then you get to a place where they can fail in weird ways. They can throw weird errors, and they might not be as resilient as you want in a real production workload. So part of what we do is we just kind of keep abreast of all that work out there, and then we use it ourselves in our inference stack. We use the kernels ourselves in various ways, so we kind of have that operational experience with the best kernels out there as well.
Okay. And in terms of the memory optimization, I think this has become very critical at scale. So can you share some
Mhm.
specific strategies that have worked for the large scale AI system, particularly the lessons from Together AI's platform serving enterprise workloads?
Yeah, great question. So the memory optimization is really a big one as you're trying to scale up these really large trillion, 2 trillion parameter models, and figuring out how to how to get them to fit on
Yeah.
GPUs. I think one set of things is of course the new optimization sorry, the new precision. So MXFP8, can you use that to train? If you can do that in FP8 instead of BF16, you kind of use half the memory that you would have used before. Can we develop algorithms for MXFP4 and VFP4? These are the new 4-bit floating precision numbers. I think the research is still a little bit out there to figure out how to use it in training. But if you can get it to work in training, then you can cut down the memory again by half. So that's on the training side. On the inference side, we work with customers to quantize their models, make sure that they actually don't lose any quality. So of course, we will help quantize and then evaluate it on a bunch of open source benchmarks. But then we also know that what the customers ultimately care about is their own use case. So we'll work with the customers and say, hey, what
Mhm.
is some representative traffic or some representative benchmarks that you really need to hit, that you really want to make sure it works in order to serve your traffic? And then we'll make sure that when we quantize the model, we can actually do that. And we also work, one of those 10 to 12 professors is the guy who basically invented quantization,
Yeah.
or at least did it in the transformer era. So we are always developing new quantization algorithms, testing them out on the academic side, trying to figure out things that work, and then bring them over to the industry and to the actual customer collaborations.
Yeah, it's interesting. Let's maybe talk about the future of the AI hardware and architecture. So we're
Mhm.
seeing the chip from the general purpose GPUs to specialized NPUs and ASICs. And how do you see this hardware evolution impacting the way companies should approach their AI infrastructure strategies?
Yeah, it's a really good question. I think so. You're seeing a rise, I think a proliferation. I think is the right word
Yeah.
of new hardware. It's everything from AMD GPUs to
Mhm.
Cerebra, Samba Nova, Grok.
Yeah.
Edge is coming out soon. I think it's a really interesting time to be working in AI. So I think from the customer standpoint, what I would advocate is first of all just a little bit wait and see. So if you're the customer and
Mhm.
you're just running inference, you don't necessarily need to go invest yourself in any of these new hardware platforms. You can let the cloud providers or the hyperscalers really try this out and see how they work. See what are the key applications where things can really benefit. There will be places where some particular chip is potentially more useful than another particular chip. If you're a new startup, you don't necessarily need to take that risk on yourself. But I'd say you should go work with a cloud partner to evaluate them to really see, will this work with my workload? And of course, on the hardware developer side, on the hardware vendor side, they're really interested in getting this feedback as well, because in each of the cases when this new hardware comes out, they designed it 2, 3 years ago,
Yeah.
and it's taken this long to actually go and print out the chips. A lot changes in 2 to 3 years. Like 2 to 3 years, attention actually looked different. So transformers actually look different. The best language models actually look different from what they look like today. So there's that mutual back and forth of, does the hardware that we designed a couple of years ago, is it going to work as well as the NVIDIA hardware? Is going to work better? Could it work better? What are the circumstances? And it's a really exciting time to kind of see that proliferation in new models, new hardware architectures, and see like where these can benefit different end user applications.
Yeah, interesting. And also your work on the efficient machine learning architectures that scale your sub-quadratically shows promise for the handling longer sequence. So
Yeah.
what does this mean for the enterprise application that need to process large document or the extended conversation, which should become a big use case right now? Yeah.
Yeah, great question. So the story behind this line of research, we put out a series of papers on state-space models and convolutional models. So these are
Mm,
kind of alternatives to transformers. And the real thing about these is that so the transformer, you can think of it as it scales quadratically in that input sequence, and it does something real actually kind of naive, where if you
mm,
have some super long document, it's going to take every word in that document and compare it to every other word and try to figure out what the
yeah,
relationship is across the entire document, which is not how humans think. It's not how we are having this conversation. It's not like every time you ask me a question, I go look up the transcript and try to figure out, oh, how does this question relate to every single word that was said in this entire conversation? So if you think about it, it's a little bit of a naive way to do language. It's done amazing things. A lot of the models that we see today do this. But we, in the, again, kind of this academic industry collaboration, we started proposing and evaluating, looking at some of these new models. Some of those ideas started to proliferate in the kind of the open source model community. So the Mythomax model looks a lot like some model that we developed before. The Mamba model that some of that tree and some of my old lab mates released also builds on this line of work, and I think it's been scaled in various ways by folks like NVIDIA and Jamba and things like this. The Quen Next model builds on some of these foundational ideas that
mm,
have been developed in academia by folks like Songlin Yang, kind of building on this whole community, this line of work, RWKV. So there's a lot of these really interesting open source models that are not just basic transformer models. And they can start to really change the performance profile. So some places I would watch out for this. So long documents, like you say, really, really important. I think makes a lot of sense for this. Like if you want to evaluate, like, all the documents in your corpus, or you're looking at long legal documents or something like this, I'd watch out for it there. I'd watch out for new modalities like video generation,
mm,
video analysis. I think the really interesting thing about these video models like Sora, WAN 2.2, Haiyuan, things like this, is that they're really compelling models, but they take so long to run. They're so expensive.
yeah,
I think you're going to see a lot of work in trying to make these models more efficient. One of our customers, Kriya, actually just released something along these lines where they're actually changing the basic architecture of their model. I think taking some basic inspiration from some of the work that we've done along these lines. So I'd watch out for there in video. I'd watch out for in long sequence, long context, like you say. Some of the more exotic applications like DNA foundation models are using this stuff all around because the human genome goes to millions of base pairs long. So you're never going to have a transformer do that. So there's a lot of these really interesting applications.
yeah, interesting. So the concentration of the AI infrastructure development among the tech giants right now raise a lot of questions about the accessibility in the future. Like, do you think how can the smaller company and startups, exist in this ecosystem? So shall they compete with this building AI infrastructure? They shouldn't build it at all, or they just work with the open source like together, and they just be the users of this AI infrastructure. Like what do you think?
That's a great question. I think for there's kind of two bits to it. So first, from the AI application, AI model side, I think it's never been a better time to build, honestly. So, and that's because the impact that a small team can have right now
Mhm.
is so much more than you could have before. Like if you're in the social media phase of things, you kind of have to build this giant user graph in order to start to compete with somebody like Facebook. In the AI world, you can just be a team of 5 to 10 people, really smart, really brilliant. Go get some compute. If you know something better about how to use the data or how to train the models or how to do something like this, you can actually have a frontier model with a large amount of investment, but it's not like you have to build a billion-dollar to or trillion-dollar company in order to compete with these companies. Like you can actually go head to head and compete with some of these frontier labs right now. So I think that is that is really great. Shops like Cursor that are really small, really agile. the frontier code generation models right now, the frontier, consumer facing code generation app. So you can really have a huge impact with a small group of people right now. On the AI infra build out side, so obviously from where I sit at Together, the first thing I would say is I would never have expected us to grow to the size that we grew, or as certainly not as quickly or as rapidly over the last 3 years. So I won't say it's impossible, because clearly, we were able to grow at this clip. But I will say that I think it is often a different set of skills than the skills that you want to be kind of building out your model. So what the thing that we found is that the folks who are really thinking about how to train these models, how to find the right data, how to change these model architectures, are maybe not necessarily the same set of people that you want building out all the AI infra and building out kind of the large data centers. One thing that Together does really well is we found that small group of people who actually excels at both things, but that can be quite an investment. So if you're one of these new companies and you're trying to scale, I think the right thing to do is to partner with someone like Together, who can really be an extension of your infra team for you. We talk to customers a lot who are like, oh, we could spend billions of dollars to go build out an infra team to go build out those people, or we could just work with Together and they can both provide us the GPUs and give us the infra support that we need.
Yeah, like SB10X, we are a happy customer. Yeah.
Yeah.
So, so last question. I think looking ahead the next 2 or 3 years, things, been getting changed very fast. Like what kind of developments in AI infrastructure that should the enterprise leaders be preparing for? Are there any upcoming Together AI initiative or industry trends that you're particularly interested or excited about?
Yeah, I think so. The macro trend that everyone is watching and talking about is just the scale of the build out that is happening right now. I think it is a industrial build out on the scale of railroads. So it's been a long time since the United States has or certainly in America, and I think around the whole world, that you've seen this. So you're seeing it here. You're seeing sovereign clouds. So there are countries that want to have a strategic investment in these places. So you're seeing a lot of these trends. I think that build out will come with really exciting improvements in the model. So and it's going to be from a lot of different places. So we've seen, I think, language models see a ton of investment, a ton of build out. We're starting to see it with the video models. We're starting to see it with the image models. I think we'll see a lot more diversity in the AI applications, the AI models that come out there. So it's not just going to be chatbots. Like, we'll get better chatbots, and I think that's always great when we have the better chatbots. But I think you're going to see the end applications get a lot more sophisticated as we build this out, as people have more compute, as people have more potential to build out stronger models. And you're going to see it from a lot more people. So part of the reason that this build out is happening is that everybody wants their slice of the 1,000 plus GPU cluster, right? Or not even their own slice. Everybody wants their own 1,000 plus GPU cluster. And what you can do with 1,000 Blackwells is really quite amazing. Like if you went back 5 years and say, hey, here's 1,000 Blackwells worth of compute, the amount of things we'd have been able to do would be insane. And now every mid-sized or small-sized AI startup is going to have access to that. And that's a really exciting trend, a really exciting build out. And I'm really excited to see what our customers build, what the industry builds, and what we can see going forward.
Yeah, thank you so much, Dan. I think it's very eye-opening hearing about the amazing things that you're working on at Together AI, and I believe the audience here who are mostly working in the enterprise to scale AI would benefit from what you share. So thank you so much.
Yeah, thanks so much for having me. It's been a really great, really fun conversation.
Yeah, thank you.
Thanks.